Hello everyone, this is the last testable module of the class. This is module M5.4 and we're going to talk about nuclear fusion and nuclear fission. Previously, we've talked about the stability of nuclei, which depends on a precarious balance between the strong force that holds the protons and neutrons in the nucleus together and the electromagnetic force, which causes the protons in the nucleus to repel each other. Due to these two competing forces and the limited range of the strong force, larger nuclei with more nucleons tend to have an overbalance of neutrons. This increases the amount of strong force present without also increasing the electromagnetic repulsion. Because nuclei are small enough to be subject to quantum mechanical effects, the exact balance of the stability of any single nucleus is really just a probability, and many nuclei have some non-zero chance of decaying in order to achieve a more stable configuration. In M5.3, we talked about alpha, beta, and gamma radiation as common types of nuclear decay. However, in more extreme cases, a more dramatic transformation occurs in the quest for greater nuclear stability. There are two such transformations that can occur: fission and fusion. Both of these transformations tend to release large amounts of energy, making them exciting areas of research for energy production. In previous modules, we also talked about how we can compare the stability of nucleons in terms of binding energy per nucleon. Nuclei with the highest binding energy per nucleon are bound the tightest, and thus they are the most stable. In general, binding energy per nucleon is highest around 60 nucleons, but of course, this also depends on how many of those 60 or so nucleons are protons and how many are neutrons. Smaller nuclei with less than 50 nucleons can become more stable by fusing together into larger nuclei to achieve a stronger binding energy per nucleon. This is called nuclear fusion. Larger nuclei with greater than about 60 nucleons can become more stable by breaking apart into smaller nuclei, each with a larger binding energy per nucleon. This is called nuclear fission. Whether or not a particular nucleus can undergo fusion or fission depends on a number of quantum properties of the nuclei that we won't go into here. But we can say that both fusion and fission will result in the significant release of energy. Although fission, or the breaking apart of a single nucleus into multiple daughter nuclei, can occur spontaneously, most often it is induced when a stray neutron is absorbed by the nucleus. This upsets an already delicate balance of energy within the nucleus, inciting it to fission into two or more smaller, more stable nuclei. Often, additional decay products are released, such as additional single neutrons or photons. Note that alpha decay is actually just a special case of nuclear fission. The alpha particle is actually just a helium nucleus. So it should not be too surprising that nuclear fission obeys the same equation that alpha decay did. In nuclear fission, the net number of protons and neutrons on each side of the reaction remain the same. There is no transformation of neutrons into protons or vice versa. So we don't have to worry about converting mass to energy and can just focus on the balance of energy on each side of the equation. As we saw in M5.3, the potential energies of all the nuclei can be translated into their binding energies, and the kinetic energy of the decay products are all combined into one quantity, which we'll call the energy released in the interaction. Let's find the energy released in the fission of uranium-235 into tellurium-134, zirconium-99, and 3 neutrons. The fission products are tellurium, zirconium, and 3 neutrons. The 3 neutrons are not bound, so they have no binding energy. The binding energy per nucleon of tellurium-134 is 8.383836 mega-electron volts, and the binding energy per nucleon of zirconium-99 is 8.540758 mega-electron volts. On the initial side of the equation, we have another single neutron that does not have a binding energy, and then uranium-235 with a binding energy per nucleon of only 7.590907 mega-electron volts. The first thing we have to do is multiply these values by the appropriate number of nucleons. Then we plug them into the equation. Assuming we have done everything correctly so far, the rest is just calculator work. The final answer is that about 185 mega-electron volts of energy is released in this fission reaction. Some of this 185 mega-electron volt energy will go to the kinetic energy for the tellurium and zirconium nuclei, but most of it will go towards kinetic energy of the 3 neutrons. If there are other unstable nuclei nearby, these neutron products can continue to go on to ignite another fission reaction. If a sample of a particular radioactive element is large enough, it can undergo a chain reaction in which the first fission reaction sets off multiple secondary fission reactions, and so on. Each fission event takes fractions of a second, so a large chain reaction can lead to the release of massive amounts of energy in a very short period of time. If the conditions of the chain reaction are not carefully controlled, the massive amount of energy released in such a chain reaction can be disastrous. Little Boy, the name of the uranium fission bomb often referred to as an atomic bomb that was dropped on Hiroshima during World War II, contained 64 kilograms of highly enriched uranium. Usually in nature, a sample of uranium is about 99.3% uranium-238 and only about 0.7% uranium-235. Enriched uranium has been processed to contain a higher percentage of the more volatile uranium-235, usually up to around 3.5 to 4.5%. So 64 kilograms of uranium that has been enriched to contain 4.5% uranium-235 will contain about 2 times 10 to the 24th uranium-235 nuclei. If all of these nuclei fissioned in a massive chain reaction, it would release 3.6 times 10 to the 32 electron volts worth of energy, which translates to 5.8 times 10 to the 13 joules of energy. For comparison, this is over 200 million times as much energy as what is released by a single hand grenade. It is actually estimated that Little Boy probably released about 63 times 10 to the 12th joules of energy over Hiroshima. Clearly, the destructive power of just 141 pounds of nuclear fuel is astonishing. This graphic shows superimposed photos of the first test of the atomic bomb, which took place at the Trinity site at the White Sands Missile Range in New Mexico. A photo of the Empire State Building has also been superimposed to the side for a sense of scale. This was the first detonation of a bomb powered by a nuclear reaction, ushering in the nuclear age. The director of the Los Alamos National Laboratory, where the bomb was designed, is said to have recalled his feeling when he witnessed the explosion by quoting the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Of course, nuclear fission power has also been harnessed for peaceful uses, such as nuclear power plants, which supplied about 10% of the world's electricity in 2018. Nuclear power is becoming safer and more efficient, with some processes to recycle nuclear waste rather than needing to store it somewhere. But it does remain up for debate whether the high yield and efficiency of nuclear power are worth the drawbacks of using radioactive material as fuel. On the other side of the binding energy per nucleon plot, we have smaller nuclei that can become more stable if they combine to form larger nuclei in the nuclear fusion process. Although this can happen spontaneously, it does require 2 nuclei with just the right properties for a fusion reaction to occur to be in the same location with very high temperatures and pressures to ignite the fusion reaction. These conditions make fusion somewhat rare here on Earth. Again, the net number of protons and neutrons does not change, so we can use the same equation for released energy that depends only on the binding energies of the nuclei involved. Also like fission, there are often other decay products present in a fusion reaction. One place where fusion occurs spontaneously on a regular basis is the interior of the sun. In fact, the energy from the sun that warms our planet, gives us light, and allows for life to exist all come from the energy released by fusion, transported to the Earth by photons, which are actually just extra decay products from the many fusion reactions. So every beam of sunlight that you enjoy is actually a stream of photons produced in the largest fusion reactor in the entire solar system. There are actually quite a few different fusion reactions that take place inside the sun. This graphic shows the hydrogen and helium fusion chains. Another major fusion chain in the sun is called the CNO cycle, which involves carbon, nitrogen, and oxygen, in addition to hydrogen and helium. On the next slide, we will calculate the energy released by 2 helium-3 nuclei that fuse together to produce a single helium-4 nucleus plus 2 hydrogen nuclei. The binding energy per nucleon of helium-3 is 2.572681 mega-electron volts. The binding energy per nucleon of helium-4 is 7.073915 mega-electron volts. It should not be surprising that two helium-3 atoms will quickly fuse into a single helium-4 atom, given the large difference in binding energy per nucleon. The two individual protons are unbound, so they do not have a binding energy. Of course, an individual proton is just a hydrogen nucleus, so sometimes you will see the 2p written as 2 hydrogen 1 instead. There are other isotopes of hydrogen that also include neutrons. Those isotopes are bound states between the single proton and the neutron, so they will have a binding energy. As usual, the first step is to convert binding energy per nucleon to total binding energy for each nucleus. This time, we have two initial nuclei, so we sum over those, and only one product nucleus. The result is a released energy of about 12.86 MeV. Although 13 MeV is much less than the 185 MeV that was released in our example of nuclear fission, nuclear fusion is more efficient at releasing energy per nucleon. The uranium-235 fission involved 235 nucleons for a rate of about 0.79 MeV per nucleon, while the fusion example involved 6 nucleons and released 2.14 MeV per nucleon. Also, fusionable nuclei like hydrogen and helium are much more naturally abundant than fissionable nuclei such as uranium and plutonium. If we could effectively harness the power of hydrogen fusion, then regular water with its 2 hydrogen atoms and 1 oxygen atom would become a powerful energy-producing fuel. If humans could successfully harness nuclear fusion as a reliable, cost-effective power supply, it would change life as we know it. Unfortunately, in order to induce fusion, the nuclei need to be confined to a space with very high temperatures and pressures, much like the interior of the sun. Scientists have achieved fusion, but the energy required to run the fusion reactor exceeds the energy released from the actual fusion. The ability to induce fusion at more reasonable and cost-effective temperatures is called cold fusion, and it is something of the holy grail in nuclear physics. In summary, fission is a process in which a large unstable parent nucleus splits into 2 or more daughter nuclei. It generates a significant amount of released energy. There may be fission products, such as neutrons or photons, in addition to the daughter nuclei. Fission occurs in elements with more than about 60 nucleons, and fission has been effectively harnessed by humans, but it comes with some drawbacks. In contrast, fusion is a process in which 2 or more small, unstable nuclei fuse together to form a larger, more stable nucleus. Fusion is more efficient than fission, releasing more energy per nucleon. There may be additional fusion products, such as protons, photons, electrons, positrons, and neutrinos. And fusion has not yet been effectively harnessed for human use, but we do still benefit from it every single day in the form of light and energy from our sun.